Before we begin our deep dive into the world of parametric design environments, visual programming languages, and various optimization approaches, it's useful to pause for just a moment and think about why parametric design and optimization has having such a big impact on the world of architecture, engineering, and construction. And fundamentally, what we want to look at is just how these new tools are transforming the way we approach design in architecture, engineering, and construction. So we're going to look at the flow of the different design approaches and really kind of think about really what changes as we move from explicit design to parametric design and finally towards generative design. So let's go ahead and get started with that. If we start with the world of explicit design, that's what I call what we typically do when we are modeling in a tool like Revit or AutoCAD, where we explicitly go through and we decide about where to place different objects and then put them into the model at those places. So if we think about the process we're using, typically we're implicitly assessing the site, the existing conditions. We're considering in our minds some of the past approaches that have been used, some of the inspirations that may be guiding us, thinking about our design goals, maybe some of the constraints, maybe even kind of thinking about some of the different alternatives. But all that typically is going on in our minds. And what is explicitly expressed and recorded is our design decisions. When we're ultimately deciding on a decision, we put that in the model or in the documents to express our design. Okay, so that process leaves a whole lot happening implicitly in our mind and doesn't leave very much explicitly in the model for us to follow up on. Now, there's a trade-off in terms of doing this. Okay, the trade-off of this explicit design where you just can place anything where you think it ought to be in a model is that you have a lot of freedom. Okay, you have freedom about what you select, you have freedom about where you go through and place things. So it's a very easy environment to work with. But we'll also find out there's a trade-off in the responsibility that goes with that, in that once we do go through and place things, it's actually pretty hard to go ahead and reevaluate or update anything. So if any of the conditions change, if it turns out the site conditions aren't right or the materials are different and we can no longer have access to a certain something that we specified, it's actually an awful lot of work to go back and change that explicit design. That work that's involved in evaluating, updating, and changing our designs often leads to solving the problem once and being satisfied with the first reasonable solution, as opposed to actually going back and considering many different solutions, because the work of evaluating those many different solutions and ultimately documenting them is just too much. And if we're not being paid for that, no one thinks it's worthwhile. Okay, so the world of explicit design is where we've lived for many years, but now we're starting to have new opportunities to start thinking about parametric design. So let's think about some examples and really how parametric design is a little bit different than explicit design. So in the example side, here are some fantastic new buildings that are being created that illustrate, things that we can do with parametric design that would be much harder to do with explicit design. So here's a fantastic new Zaha Hadid creation. You can sort of see the outer shell of that building is incredibly complex. And if we had to go through and model that all kind of explicitly, one bar at a time, we probably wouldn't come up with such an expressive form or be willing to kind of go through all the iterations that would be necessary to actually optimize all those different members. Again, here's another example of a nice canopy structure that's being proposed that, again, was possible with parametric design. We can describe that mathematically and then use a little bit of machine programming to figure out how all those structural members would be. But it would actually be very hard for us to go through and plan that all by hand, model that by hand, and then if we ever had to change anything, to go through and change and rework that design would be very, very cumbersome, so we probably wouldn't do it. Okay, here's another example just from the news the other day. This is the Jing Gang Studios' new proposal for an addition to Chicago's O'Hare Airport. And as you look at what's going on with that roof structure and the general form, that would be very hard to model by hand explicitly. Okay, but if we start using parametric design approaches, we can sort of get the fluidity and the flexibility to create these very fantastic structures, testing a lot of different alternatives and ultimately deciding upon the one that we think is going to be the best solution to the design problem. So as we think about parametric design, one of the most important aspects is just thinking about how we specify the solutions. Okay, when we are explicitly designing, okay, we actually express the decision, the final decision, we record the final decision. Okay, and that's what's actually carried in the model and carried in the documents. When we're thinking about doing parametric design, we actually want to back up a level. And rather than sort of being worried about encoding a final design decision, what we really start thinking about is, can we embed the intelligence in the model through assigning rules so that if we had to make that decision again, we could make that decision automatically. So it's less about the result and more about the rules that give us that result. And being able to encode those rules and embed that intelligence in the model gives you all sorts of power to go ahead and rapidly flex and test different alternatives. Now, when we're doing parametric design, a very important first aspect is that we have to identify the input parameters. That is, all the different things that we want to test. So what are the design inputs? What is it that we are willing to flex, to test, to try? We can't vary every aspect of a design, so we have to choose the ones that we are willing to flex and that we want to see the results of testing. Okay. And then within parametric design, the tools give us the ability to easily test the alternatives. So when we create a parametric design, we set it up in a way that we can flex or tweak those input parameters and then iterate to test a lot of different options. Now, we can manually iterate, okay, where we humanly guide each of the different design options that we're willing to consider. We can automatically think about iterating through some test options where we use a little bit of machine guidance and a little intelligence to help us figure out what are the options that would be the most productive to test. And we can even start thinking about new hybrid interfaces, which are really more about man-machine design and how we can work together, getting a little bit of insight from machines, but then still using our human insight to go ahead and really make the design decisions about which ones we want to test. Now, parametric design is really just the start of it. The parametric design is giving this option of going through, of expressing our designs in a way that can be parametrically flexed so we can see what the results would be. Optimization takes it a little bit further. Optimization is really all about trying to figure out really what is the best solution. So again, we're going to start by choosing some input variables. We're going to evaluate some alternatives, but then we're going to get to this whole issue of really what is the best alternative or best solution? What is the best alternative we might want to follow? So as we choose our input variables in our optimization schemes, what we're really doing is defining the solution space. And we can think about that solution space having a single dimension. When we talk about a single dimension optimization, it's typically one variable that we're changing versus multiple dimensions, okay, that would have 2 variables or 3 variables. But as you increase the number of dimensions, increase the number of input variables, realize that the solution space gets very big, geometrically, I guess. Basically, yeah, for every additional variable, you're going to multiply the number of different options there, and you have a very large solution space very quickly that has to be considered. Now, we want ways of evaluating the potential alternatives. Part of optimization is we have to have some way of evaluating really how good these different potential solutions are. We're going to have to choose some evaluation criteria and then ultimately define some objective functions to help us figure out how we're going to quantify those criteria. So if we think about the evaluation criteria, we might be thinking about some of our architectural goals. So aesthetically, we could think about the number of corner offices, how high are the ceilings, how open the space feels. We could think about things like, the solar insulation potential or the potential for some solar gain that we have to go ahead and guard against, or whether the design actually provides some solar shading. We can think about the wind and its resistance and the wind power potential or the ventilation that might be created. We can think about it from a LEED perspective and think about the materials that are being used, the energy performance of those, and how that actually affects LEED or even the daylighting that's available. So there's a lot of different potential goals we might have, and the idea is that any of these different goals might lead to a criteria by which we could judge the design and figure out whether we think it's a good design or not. Structurally, similarly, we could think about many different criteria: the weight of the materials, the amount of sway or deflection in the structure, the safety factors that are embodied in the structural design, the complexity of the connections, the standardization of the structure. There's a lot of ways we can evaluate a potential structural scheme and ultimately quantify how good we think it is. From a construction standpoint, we often think about the time it takes to construct things, the cost to construct things. We often think about the quality and think about those as being a trade-off. But also now we often think about the prefabrication potential and really tend to favor, if we like the idea of prefabrication, designs that have a very good prefabrication potential. But we could also be thinking about the operational goals for the project or the financial goals. The big point here is there are a lot of different goals we might want to consider as evaluation criteria, okay? And what we have to do is really come up with some objective functions, some way of measuring the design, some way of quantifying the design, and have to decide for each of these different goals, is that something we want to maximize or is that something we want to minimize? Okay, but we need to go through and evaluate our designs. Once we've evaluated our designs across all the different criteria that we're willing to consider, we then get to the idea of needing to go through and identify a best solution. So let's think about that. There's several different aspects to think about. There's this whole notion when we talk about optimization of the timing. Will you decide on what's best in advance? That's called a priori optimization. Or are you going to basically figure out after the alternatives have been generated which of those is the best? That's called a posteriori. So either you sort of know what you're looking for in advance, or you could be just generating a lot of alternatives and choosing the best amongst the ones that got generated. Another important kind of way of thinking about optimization is the whole notion, is it a single objective optimization or a multi-objective optimization? Okay, single objective optimizations tend to be fairly easy because you're really just trying to solve for one thing that you're either trying to maximize or minimize. If you have multiple objectives, the space gets much more complex very, very quickly. And often with multi-objective optimizations, we'll try to come up with a single answer by weighting, creating some sort of a weighted average of each of the different objectives. Or we could actually try to maintain multiple answers, really think about all the different evaluations for each of the different objectives, and then come up with some way of visualizing that. So as we think about visualizing things, we can come up with, charts that show Pareto frontiers, for example. That's the idea that there are a number of different objectives and there's a frontier at which all the different potential combinations of the different results are equally attractive. Beyond that, things are infeasible. Okay, below that, things are, well, just not achievable. So we go through and kind of think about what that frontier is and try to think about really where we want to be on that frontier. Another way we sometimes try to visualize this is with spider diagrams, where we try to map out all the different objectives and just sort of provide the evaluation against those objectives. Okay, these are both sort of valid approaches, but you can imagine as we try to move through multi-objective spaces that have n dimensions, how hard it is to visualize and kind of the results and really try to figure out which is the best solution. Now, not only can we sort of identify what we think is the best solution, we can actually start thinking about optimization as a way of evolving new alternatives. And there's a lot of very cool research going on right now that's all about genetic algorithms and how we can do this iteratively, where we think about each successive generation of evaluations giving us some feedback that'll guide further exploration. So what we try to do is use some genetic algorithms which give us the ability to generate new cases that we'd like to test based on the inputs that gave us the strongest results from the prior generation. So you can think about why that's called genetic as an algorithm. It's very much like the whole notion of evolution and kind of heading towards the dominant traits that will ultimately win out. But we can try to basically, based on prior feedback, evolve new test cases that we'd want to try. And this is kind of a very efficient way of trying to find the most efficient solutions. Now, with the whole realm of parametric design and optimization, as of today, people are using these sorts of tools to give us design assistance. That's just to help out. If, for example, you're designing that airport terminal and you want help coming up with a good structural scheme that'll allow you to create different forms and lay out the trusses for you, that's design assistance. You basically are just getting some assistance at trying to design something. Okay, and the tools are helping you do that. There's design verification. That's where we could actually use the tools to verify that the rules are being met, the code requirements are being met. We're just basically checking a design to make sure that it meets all of the specific requirements we want it to. Okay, and at the highest level, we get more into design optimization. That's really the whole notion that your design tools are going to help us try to identify and even generate new cases that are going to help us find the best possible alternatives, maybe even ones that we haven't thought of otherwise. Which leads us to the emerging application, really where the frontier of this research is now, and that's in generative design. So generative design takes optimization even one step further. The idea is that what you're going to do is, rather than thinking about all the inputs and the constraints and trying to come up with a solution, okay, if you really stop to cast the problem in terms of what is the fundamental objective you're trying to achieve, okay, and then give many different input variables and let computers actually try to generate alternatives to see if they could come up with designs that could maximize those objectives. Like really, what would happen? What would you get? Okay, so it's a little bit strange to think about it this way, but it's actually very liberating if you think about really just what does the object you're trying to design have to provide, not worrying about how you do it, and let the machines actually go through and generate an awful lot of different alternatives that you might not even consider. So there is some really cool research being done in this area. There are some links here within the mind map to kind of point you towards an overview of the generative design process, how we're using it in manufacturing, as well as in our AEC. Okay, there's actually even a paper that's been published here about generative design in architecture and construction, so you can follow the link and kind of find it on the Autodesk website. There are a couple of really cool projects that Autodesk is working on that I want to make you aware of. One's called Project Dreamcatcher. That's all about generative design in general and really all the capabilities of that, following everywhere from design through the creation of alternatives, ultimately through the production process. Another really good one that we're actually going to play around with in class is called Project Refinery. Project Refinery is an optimization tool that, again, will help us use genetic algorithms to go through and evaluate many different alternatives and ultimately generate new alternatives based on the results of some of the past work. Okay, so a lot of cool things and some videos you can watch to kind of see how you could apply these. These are some examples of outputs that have come out of generative design. You see, these are different little machine parts, and they look very organic. They look a little bit unusual. These are all about really trying to go ahead and optimize the materials placement and minimize the weight, but still provide the essential structural functionality that you need. So for example, up here, here's a machine part. You see it has like 4 kind of corner pieces that are spinning around sort of central hub. But notice that the rods in here are very different. They look very skeletal, almost, like bird skeletons, something like that. The idea is we want to minimize the weight. So what's happening is the material here is only being applied where it's necessary to provide the structural support. So we're not going through and designing something based on a manufacturing process. And the ease of kind of creating this. We're optimizing just based on trying to minimize the weight and the structural integrity. And you can see you can come up with some very unusual forms that you probably wouldn't have considered, okay, if you had to come up with this on your own. In the same way, here is, I believe this is actually a design of, it almost looks like a car chassis or some sort of link. But again, you see it's kind of a very skeletal structure that doesn't look like something you would design necessarily if you kind of came at it from the world of, what can easily be manufactured using conventional processes. But And that is allocating the material to just where it's necessary. And the idea is that you might not have thought about doing that on your own, but the generative design algorithms can go through and figure that stuff out because they're really good at not thinking within the constraints that we typically approach design problems with. They just really focus on finding the best solution to meet our objectives. Okay, as you think about generative design, it's important though, you can't just turn machines loose. You can't just turn computers loose and say, hey, do your best job and hope for the best. The important thing is you have to learn to ask the right questions. So before you start the machine designing things, you have to figure out really what you're going to guide it into doing, just how, what questions you really want answered. It won't figure that out. That's where the human intelligence is still really important. And if you start thinking about or worried about, will designers become obsolete in the future, go ahead and comfort yourself in this way, in the sense that a robot is not a craftsman. Robots can do certain things. They can certainly replicate things and do things very efficiently, but they're not exactly craftsmen. There's a difference there. An algorithm, machine algorithm, is not a designer. So there's always going to be a need for designers to work with machines, okay, to help guide those algorithms. Because somewhere between the efficiency of the machines and the insight of the humans, there's probably the best hybrid solution that works together. If you think about the advantages of generative design and why people are so excited about it as a possibility, one of the big ones that's really driving all of this is the whole notion of creativity. The idea with generative design is you can really start to explore the blind spots. We all have blind spots based on what we've seen in the past and what we expect to have happen. So we tend to limit ourselves in terms of the options that we explore. And the idea is that the generative design algorithms don't really have those blind spots. They were quite willing to go down all sorts of paths that we might not consider. And in exploring those blind spots, they might actually sort of discover some interesting solutions that we wouldn't even have brought to the table. So creativity is definitely one of the advantages we're hoping to see there. But there's also an efficiency advantage. If you think about the time to solutions, we've been trying to approach this by just adding processing power. So as opposed to having a single computer, which tends to be slow, when you have to generate a lot of solutions, we've been using an approach of adding processing power through cloud servers. So you have multiple different servers working simultaneously. That's faster, but it's still pretty much a linear solution. So you just have to keep on adding servers to give yourself more processing capability if you want to generate more solutions. The idea with the generative approach is that we can actually start doing it in a much more efficient way. That's not just about raw power, it's more about really using insights, so we can just really approach the finding of the solutions just with more insight, doing it kind of in a quicker way, okay, based on sort of just very kind of what insightful thinking. Okay, as opposed to just kind of a brute force approach of adding a lot more processing power. And the net of all that is that if we can actually come up with a shorter time per solution, okay, we can actually then consider more alternatives. We can explore a bigger design space and we won't feel constrained. So winding way back to the start of all this, you might remember when I was talking about explicit design, I said that one of the real disadvantages or limitations was that it was so much work to express our designs and explicitly put everything out there in a model that very often we would stop after one alternative minimally met the solution because we didn't really have the time to go through and consider more alternatives and fully express them. Where as you start thinking about generative design, it really turns that all 90 degrees and says, hey, if we had a very short solution time and we can consider as many alternatives as possible, as we could possibly conceive, couldn't we actually come up with sort of more creative or better solutions? And really that's where the promise of all this is. So as we roll on back and we think about explicit design through parametric design, through optimization, and ultimately generative design, there is this huge transformation that's going on that's very exciting. And that's really part of why we're taking this course and why so many folks are really looking for folks that have this skills set so that you can bring this to the design world and help lead them into the new future of using these kinds of tools to really innovate in the whole AEC process.